Heat from fire warmed mankind long before recorded time. As centuries passed, we learned how to control the fire, to better warm the spaces in which we live. Ours is an unending search to produce heat safely, economically, and as needed. As technologies evolve to better meet one of mankind's most basic needs, understanding will unlock the doors to a more comfortable future for all of us. Welcome to this General Training Heating Program.
Modules 1 and 2 presented an introduction to the basic principles of gas furnaces. Module 3 covered an introduction to gas-fired furnaces, which linked the basic principles to an overview of furnace design, types, applications, and operation. Module 4 discussed the theoretical principles of gas burners, their components, and flame and combustion characteristics. This module, Gas Controls, focuses on the controlled combustion process. Gas controls, the manual and automatic valves and regulators which control the flow of fuel gas to the orifice and burner, will be explained. The function and operation of various gas controls will be included. In their broadest sense, gas controls also include the gas ignition systems and some of the safety controls used to regulate combustion in a furnace. Because of the amount of material involved in the full coverage of furnace control systems, the material has been split into 3 modules. Besides the information included in this module, Module 6 covers gas ignition systems, and Module 7 covers furnace safety and operating controls. In this module, we will cover gas pressure regulators, devices that maintain a constant gas pressure in the gas line to the furnace or in the gas manifold upstream of the orifices. Manual and automatic gas valves, devices that control the flow of gas to the furnace, the pilot, and the burners. Combination gas controls, devices that include manual and automatic gas valve and gas pressure regulator functions all in one assembly. It is extremely important to understand the application of a gas control because arbitrarily changing one for another can lead to trouble. Gas controls are carefully selected for a furnace application by the manufacturer for proper function and safety. Therefore, only replacements recommended by the manufacturer should be used. Another important consideration is the great variety of control designs available. Gas furnace manufacturers have changed controls from year to year and model to model. Their aim has always been to produce the most reliable and best performing products with the latest technology. Because of the large number of control variations, it's impossible to cover all controls. Therefore, selected examples will be used to explain generic operating principles, adjustment and checkout procedures that apply to most of the gas controls in common use today. The function of gas pressure regulators is to reduce, adjust, and maintain gas pressure downstream regardless of the gas supply pressure upstream. There are 3 pressure regulators used in a typical gas heating system. The first, the service regulator, is used in the gas supply line to regulate pressure to the gas meter and line supplying the furnace. The second, the gas manifold pressure regulator, is located next to or inside the furnace to regulate the gas pressure to the gas valve and manifold. The third is sometimes used to regulate gas pressure to the pilot. Variations in utility supply line pressure are common, and pressures may be too high for direct connection to a gas furnace or other gas appliance. Therefore, a service regulator is required to reduce, adjust, and maintain the pressure being supplied to the appliances in a building. For natural gas, This regulator is usually provided by the gas utility and installed upstream of the gas meter. It should be adjusted by the utility to supply a pressure of approximately 7 inches of water column at the inlet of the furnace when the furnace is operating. The pressure supplied to the furnace should never exceed the maximum pressure on the furnace rating plate, which is about 13.5 inches water column. Also, the pressure supplied to the furnace should not be less than the minimum of 4.5 inches to assure that the furnace can be fired at rated input. LP gas service regulators are installed at the gas storage tank by the supplier and set at 11 inches water column. They should only be adjusted by the gas supplier. Gas furnaces are designed to operate with manifold pressures somewhat lower than the supply pressure. This allows for pressure drop in the gas piping and assures that there will always be adequate pressure to operate the furnace at its rated input. All natural gas furnace installations have a pressure regulator to control manifold pressure. On most furnaces, the pressure regulator is built into the combination gas valve. However, you may find some furnaces with a separate gas pressure regulator located on the manifold upstream of the automatic gas valve. On others, it may even be located just outside of the cabinet. Wherever they are located, they all function the same way. Furnace pressure regulators for natural gas should only be adjusted when the furnace is operating. They are usually factory set for a manifold pressure of 3.5 inches water column and may be adjusted on-site within the range of 3.2 to 3.8 inches water column for rated input. For LP gas, there is no manifold regulator. The service regulator on the tank controls the manifold pressure. If there is a regulator in the gas valve, the manifold pressure should be adjusted between 10.5 and 11 inches water column for rated input. Manifold pressure can be measured with a water manometer connected at the pressure tap located either on the manifold or on the automatic gas valve. A typical gas pressure regulator operates the same whether it controls the supply line pressure or manifold pressure. A regulator consists of a flow modulating valve connected to a spring-loaded diaphragm. The diaphragm senses the difference between the outlet gas pressure below and the atmospheric pressure above. The resulting force on the diaphragm pushes upward against the spring, adjusting the position of the valve to modulate the gas flow. This is an important concept to understand because it's the outlet gas pressure that is to be held constant with respect to atmospheric pressure. The outlet pressure under the diaphragm working against atmospheric pressure and spring force above acts as the closing force on the flow modulating valve. The spring force can be adjusted by turning a screw. When the downward force of the spring is equal to the upward force of the outlet gas pressure on the diaphragm, the regulator is in equilibrium, setting the partially open position of the valve to control the gas flow and hold the outlet gas pressure constant at the desired setting. The diaphragm and spring remain in equilibrium until there is a change in the inlet or supply pressure or a change in the rate of gas flow through the regulator to the appliances. It's important to understand that the regulator only functions when there is flow through it. A decrease in the gas supply pressure reduces the outlet pressure under the diaphragm, reducing its upward force against the spring. As the spring becomes the stronger force, it begins to push the valve downward, permitting more gas to flow through the valve. This increases the outlet pressure back toward its initial setting. The increased pressure under the diaphragm acts against the spring force to close the valve. These forces come into equilibrium with the valve slightly more open than before the line pressure decreased, but with the outlet pressure held constant. An increase in gas flow through the regulator causes a similar response in the regulator. If, for instance, a second appliance turns on, the supply regulator must pass more gas but keep the outlet pressure nearly constant. When the second appliance comes on, the regulator outlet pressure starts to drop, reducing the pressure under the diaphragm and resulting in a new equilibrium point with the valve slightly more open and the outlet pressure constant. Note, if the line pressure decreases too much, the regulator may not be able to maintain adequate manifold pressure. An increase in the gas supply pressure increases the pressure under the diaphragm, pushing it up and closing the regulator valve to reduce the flow. As the outlet pressure is reduced, the spring and diaphragm forces come into equilibrium with the valve slightly more closed than before the line pressure was increased. The outlet gas pressure remains constant at its original setting. A decrease in gas flow through the regulator acts in a similar manner. For instance, if one appliance shuts off, the outlet pressure increases. The increased pressure under the diaphragm tends to close the regulator valve and to reduce the flow and the pressure. A new equilibrium point will be established with the valve slightly more closed. The outlet pressure remains constant at its original setting. A vent opening is needed on a regulator to assure that atmospheric pressure reaches the top of the diaphragm. For safety reasons, the vent opening must be relatively small to minimize the rate at which gas could escape in case of a diaphragm leak or a ruptured diaphragm. To control the rate of gas escape to a safe level, most regulators have a leak-limiting orifice incorporated in the vent. This orifice is sized to permit the diaphragm to move easily, yet allow only a very small amount of gas to bleed through the opening in case of a leak. Important: the vent opening must be kept open for the regulator to work properly. If a leak-limiting orifice is not used and the regulator is indoors, a vent line must be installed to carry any escaping gas to the outdoors or into the pilot flame where it can be burned safely. Again, the vent line opening must be kept open for the regulator to work properly. To change the pressure setting of a gas pressure regulator, turn its adjustment screw in or out. This varies the spring force exerted on the diaphragm. To increase the pressure setting, turn the adjustment screw clockwise. To decrease the pressure setting, turn it counterclockwise. Important: gas pressure adjustments can only be made when there is gas flow to the appliance and should never be made without using a manometer or pressure gauge to measure outlet pressure. For pressure regulators controlling manifold pressure in the furnace, pressure taps are provided either on the combination valve or the gas manifold for connecting a manometer or gauge. Gas valves control the gas supply to any section of the system piping or to an appliance. Gas valves can be either manual or automatic. All gas supply lines and furnaces must be equipped with manual shutoff valves for service and safety. An accessible manual shutoff valve must be provided by the utility in the gas supply line upstream of the supply gas pressure regulator and meter. Also, it is required that an accessible manual shutoff valve be installed within 6 feet of the furnace for service and safety. A manual main gas shutoff valve is required in the furnace upstream of the regulator and automatic gas valve to shut off the gas supply to the main burners. Pilots may be provided with a separate shutoff valve. The manual main gas shutoff valve is either built into the automatic combination gas valve or separately installed on the manifold upstream of the gas pressure regulator. Manual shutoff valves also are used for the pilot gas line. They may be separate or built into the automatic combination gas valve. On non-100% shutoff systems, they connect into the gas line upstream of the manual main shutoff valve so that shutting off the main gas will not shut off gas to the pilot. All separate manual shutoff valves are of the quarter-turn plug cock type. This type of shutoff is open when the hole in the tapered plug lines up with the piping. The hole is the same diameter as the inside diameter of the connecting piping, so that the gas flow has minimum disturbance and pressure loss as it flows through. Turning the handle or plug 90 degrees closes the shutoff valve completely. From the outside, you can tell that the shutoff valve is open when the handle or wrench lug lines up with the piping or gas flow direction. The shutoff valve is closed when the handle is positioned crosswise to the piping or flow direction. This type of shutoff valve does not require any packing or external seals to prevent gas leaks. This is because the tapered plug fits so precisely in the tapered bore of the body that it forms a gas-tight seal. A retaining spring holds the tapered plug tightly against the tapered bore. Usually, a silicone grease is used between the plug and body to ensure the gas seal and to provide lubrication for easier rotation of the plug. An automatic gas valve consists of a valve and an actuator that control the supply of gas to the burners of an appliance during operation. Automatic gas valves usually are of the disc-on-seat type. The main parts are the valve body, valve seat, valve disc, valve stem, return spring, and actuator. The actuator is an electrical device that lifts the valve disc off of the seat when it's energized. Gas flows through the valve when the disc is lifted off of the seat. When the valve closes, gas pressure from the supply line and the return spring holds the disc against the seat, ensuring a good seal. However, to open the valve, the actuator must have enough strength to overcome the force of the gas pressure on the disc as well as the force of the spring. Safety codes require that automatic combination gas valves must incorporate 2 or more automatic valve mechanisms in series along with a pressure regulator and manual valve. These valves are called redundant valves because both valves would have to fail open in order for an unsafe condition to occur. However, single-seat type automatic gas valves may be found on older installed furnaces. The operation of redundant gas valves will be discussed in detail later in this module. In the next section, the basic actuator mechanisms found in automatic valves are covered. All of the valve mechanisms used in automatic gas valves are classified by the type of actuator used to lift the disc off of the seat. Common gas valve actuator classifications are solenoid, magnetic diaphragm, bimetal diaphragm, bimetallic direct opening, thermocouple. The direct-acting solenoid gas valve is normally closed when the solenoid coil is de-energized. This means that the valve closes when power is interrupted. When the coil is energized, the magnetic force generated by the coil attracts the iron armature on the valve stem and lifts the valve off of the seat. The valve stays open as long as the coil is energized. Rubber or plastic seats are used to improve sealing and to eliminate closing noise. These are often called soft seat valves. Some valves use a spring above the armature, while others are filled with oil to eliminate the opening noise. The amount of force needed to overcome the gas pressure and to lift the valve off of the seat is proportional to the valve seat area. However, the amount of force needed to hold the valve open is much smaller. This means that a large valve needs a large solenoid coil only for opening. The problem is that large solenoid coils draw more power and may need special cooling. The pick and hold concept provides one solution to large valves. This design has 2 solenoid coils. The powerful pick coil and the less powerful hold coil are used together to open the valve. Once the valve is open, the pick coil is de-energized and the lower power hold coil remains energized to hold the valve open. How the pick and hold feature may be incorporated into the electrical safety circuit of the furnace will be discussed later. The magnetic diaphragm uses a small solenoid valve in combination with a diaphragm valve to get around the seat size limitations of a direct-acting solenoid. The diaphragm utilizes gas pressure as the primary force to open and close the main valve port. The solenoid operates a relatively small valve in a bleed line to the diaphragm. When the solenoid coil is de-energized, the valve is closed, and the solenoid actuator lever holds the bleed line valve against the bleed port, causing it to close. The bleeder valve is a two-way valve. When the bleed port is closed, the diaphragm pressure equalizer port is open, allowing gas to flow into the chamber above the diaphragm, equalizing the pressure on both sides of the diaphragm. This allows the valve disc to drop to the main valve seat and shut off gas flow. The gas pressure above the disc provides the force to hold the valve closed. To open the valve, the solenoid coil is energized. Its magnetic field pulls the actuator lever against the coil, pushing the bleeder valve down. This action opens the bleed port and closes the pressure equalizer port. The gas above the diaphragm can now escape through the bleeder port, while no new gas can flow in above the diaphragm. Once the gas pressure above the diaphragm bleeds down to atmospheric pressure, the gas pressure under the diaphragm exerts a force to lift the valve disc off of the seat, allowing gas to flow through the valve. On this type of valve, a vent line must be connected from the bleeder port to the combustion chamber or pilot so that the bleed gas can burn safely. If the vent line or bleeder port becomes plugged, the valve will not open. The next two types of valves discussed use a bimetal actuator. First, let's look at the basic operating principle of a bimetal. To construct a bimetal, two strips of dissimilar metal are fused together along their entire length. All metals expand when heated and contract when cooled. However, the amount of expansion or contraction is different for each metal for a given temperature change. When heat is applied to a bimetal strip, one metal expands more than the other. Since the two metal strips are fused together and cannot separate, the bimetal strip warps or bends into an arc because of the greater expansion of one metal. If one end of the bimetal is fastened in place, the other will move back and forth as it's heated and cooled. This movement can be harnessed to operate various devices, such as valves and electrical switches. A bimetal used this way is sometimes called a heat motor. The bimetal diaphragm valve is very similar to the magnetic diaphragm valve, except that the bimetal diaphragm uses an electrically heated bimetal to operate the bleed valve instead of a solenoid. The bimetal is heated by a small electric resistance heat element placed on or near it. The heat warps the bimetal, producing a force that opens the bleed valve to allow the gas above the diaphragm to escape. Then, as in the magnetic diaphragm valve, the higher pressure under the diaphragm lifts the valve disc off of the seat, allowing gas to flow through the valve. When the electric heat element is de-energized, the bimetal cools and straightens to its original shape, closing the bleed valve port and opening the pressure equalizer port. Gas then flows in above the diaphragm, equalizing the pressure and allowing the main valve disc to close. This shuts off the gas flow. Because it takes time for the bimetal to heat up or cool down enough to operate the valve, a time delay occurs in opening and closing this type of gas valve. This delay is usually about 15 to 20 seconds. Although the delay is not a problem on standing pilot-type furnaces, it is unacceptable for furnaces with direct ignition. These ignition systems need a quick opening and closing valve, such as the pick and hold direct solenoid valve or the magnetic diaphragm valve. Another application of bimetal actuators is in direct-acting bimetal valves. In these types of valves, the warping action of a heated bimetal is used directly to lift the valve disc off of the seat. A small electric resistance heater is used to warp the bimetal and open the valve. As with bimetal diaphragm valves, these valves have delayed opening and closing due to the time necessary to heat up and cool down the bimetal. This makes them unsuitable as main gas valves for direct ignition. As with the direct-acting solenoid, these valves are limited by the relatively small force generated by the bimetal. Consequently, they are better suited to smaller valve applications. A thermomagnet, much like a solenoid coil, is often used with thermocouple safety pilots to operate the safety valve in 100% shut-off automatic valves. The thermocouple, heated by the pilot flame, generates a small electric current, which is sufficient to energize the thermomagnet holding coil. The magnetic force of the thermomagnet coil is too small to pull the safety valve disc open directly, but it does have enough force to hold the valve open once it has been opened manually. For this reason, the safety valve must be manually opened and held open during the time it takes to light the pilot and heat the thermocouple enough to generate the current that holds the valve open. If or when the pilot goes out, the thermocouple cools and its current drops to a point where the coil magnetic force is too weak to hold the safety valve open, and it drops closed, shutting off gas flow to the burners and pilot. The furnace remains off until the pilot is manually reignited. Stop. Complete skills check number 1 in your workbook. Check your answers against the answer key. Identify those areas in which you need additional work. Use the paragraph references to review this material. In the previous sections, the basic operating principles of gas pressure regulators and gas valves were covered. The application of these principles in typical gas control devices was also included. Now we will focus on combination gas controls most commonly used on gas furnaces. Combination gas controls are devices that include manual and automatic gas valve and gas pressure regulator functions in one assembly. The functions may be combined in several different arrangements to meet different requirements. In the sections that follow, we will cover the most common types of automatic combination controls, including those with non-100% shut-off valves, 100% shut-off valves, redundant valves, and two-stage redundant valves. Combination gas controls provide all of the gas control functions in a single compact device. The design of combination valves varies considerably between manufacturers, but the basic functions provided always include manual main and pilot gas shutoff, pressure regulation, pilot gas adjustment, and automatic main gas shutoff. Also provided are taps for gas supply and manifold pressure measurement, and fittings for connecting the pilot gas tube. Combination gas control designs also vary depending on the type of gas or ignition system being used. Besides the basic functions above, they also may include non-100% and 100% shutoff, redundant automatic main valves, and multi-stage valves. These combination gas controls are sometimes also referred to as automatic combination valves. The non-100% shutoff function means that the safety control shuts off only the gas flow to the main burners in case of a pilot outage. Gas will continue to flow to the pilot whether it's lit or not. Non-100% gas valves were used for many years on natural gas furnaces installed both indoors and outdoors. However, for improved safety, all furnaces produced after November 1989 are required to have 100% shutoff. Let's look at one of the simpler types of combination gas controls with the non-100% shutoff function. You would find this type of gas valve installed in natural gas furnaces with standing pilots manufactured before 1989. This combination control has a manual gas valve with a knob, a pressure regulator, and a heat motor or bimetal actuated main gas valve. When the knob on the valve is turned to pilot, gas flows through a groove in the manual valve and then through the pilot filter chamber and the pilot tubing to the gas pilot, where it can be lit manually or automatically. All pilots are equipped with a safety device that prevents the main gas valve from being energized and opening automatically until the pilot is lit. The pilot's safety device also closes the main gas valve if the pilot goes out. The pilot's safety device will be covered in more detail in Module 6, Gas Ignition Systems. Once the pilot is lit, the knob can be turned to the on position. Gas will continue to flow to the pilot. Gas will also flow past the pressure regulator valve seat to the area above the diaphragm and on to the main gas valve chamber. As the gas pressure builds up on the regulator diaphragm, it causes the regulator valve disc to close until the main gas valve is energized. When the main gas valve heat motor is energized, the valve begins to open. The gas pressure above the gas regulator diaphragm will decrease, permitting the regulator valve disc to open and establish a regulated outlet gas pressure. A regulator adjustment screw is used to adjust the spring pressure to set the proper manifold gas pressure. If the pilot goes out, the pilot's safety device de-energizes the main gas valve heat motor, closing the main gas valve and shutting off the gas to the burners. However, the gas continues to flow through to the pilot until someone manually turns the manual valve off. Remember, this is a non-100% shutoff valve. Although natural gas is lighter than air and normally disperses, there are safety concerns about gas collecting in the combustion chamber when the pilot is out. Important: before attempting to relight the pilot, always turn off the pilot gas at the valve knob and wait at least 5 minutes for the gas to clear out. The 100% shutoff function means that all of the gas to both the pilot and the main burners is automatically shut off if the pilot goes out. This arrangement utilizes two valves in series: the safety gas valve, which shuts off all gas flow to the burners and to the pilot in case the pilot goes out, and the main gas valve, which controls the normal on-off operation of the main burners. Use of the 100% shutoff function has been a long-standing safety requirement for LP gas furnaces installed indoors. It prevents the heavy LP gas from collecting in dangerous quantities in the combustion chamber or around the furnace in case the pilot goes out. 100% shutoff has been a requirement for all furnaces since 1989. In addition to the manual gas valve, the pressure regulator and the main gas valve, the 100% shutoff combination control has an internal 100% safety shutoff valve upstream of the manual gas valve and the pilot connection. This valve is manually opened during the lighting process and is held open by a thermomagnet or holding solenoid energized by the lit pilot. If the pilot goes out, the safety shutoff valve will drop closed, stopping the gas flow to both the pilot and to the main gas burners. This is what is meant by 100% shutoff. The following steps are used when lighting a pilot with a furnace equipped with a 100% shutoff type valve. The first two steps are very important for your safety. 1. To be sure that the main gas valve stays closed when lighting the pilot, always turn the thermostat to off or set it low. 2. To be sure that there is no gas in the combustion chamber, turn the main manual valve knob to off and wait 5 minutes. 3. Turn the main manual shutoff knob to the pilot position and depress it to open the safety shutoff valve. 100% shutoff valves require that the internal safety shutoff valve be manually opened in order for gas to flow to the pilot. Note that on some types of valves there may be a separate button which must be depressed instead of the shutoff knob. In either case, this allows gas to flow to the pilot. 4. Light the pilot manually. 5. Continue to hold the knob or button down for about 45 seconds until the pilot safety switch or thermocouple is hot enough to hold the valve open. To continue the lighting steps, 6. Release the button or the knob and check to see that the pilot stays lit. If it goes out, you will have to start over and wait longer. 7. Turn the main manual valve knob to the on position once the pilot is lit and the safety circuit completed, or the thermomagnet energized. 8. The pilot gas continues to flow. The gas can flow to the main burners whenever the downstream automatic valve is energized electrically. If the pilot flame goes out and the thermocouple or pilot safety switch cools, the safety shutoff valve closes, shutting off all gas flow. The gas valve cannot open again until the pilot is relit. Safety codes require that all furnaces produced after 1989 have 100% shutoff valves. The 100% shutoff valve with thermocouple pilot discussed earlier meets this requirement, but it requires manual relighting of the pilot and will not work with automatic reignition systems. The redundant valve has been designed to provide 100% shutoff with automatic reignition pilot or direct burner ignition systems. Redundant means 2 fully automatic valves in series. Let's look at a redundant automatic combination gas valve installed with a reignition pilot system. In this design, a solenoid-operated redundant gas valve is located downstream of the manual gas valve and in series with the main gas valve. When the redundant valve is open, gas can flow to the pilot and the main gas valve. A similar redundant automatic combination gas valve is available for use with hot surface type direct burner ignition systems. The valve has the pilot connection blocked. When there is a demand for heat, the pilot igniter and the redundant gas valve solenoid are energized. The redundant valve opens, allowing gas to flow through the pilot filter and tubing to the pilot. After ignition takes place, the pilot flame heats the pilot safety device, energizing the main gas valve solenoid. The main solenoid opens, admitting gas to the pressure regulator and to the underside of the main valve diaphragm. Gas pressure under the diaphragm opens the main gas valve, but the pressure regulator controls the position of the diaphragm to maintain proper manifold pressure at the valve outlet. When the demand for heating is satisfied, both the redundant and main valves are de-energized. Gas flow to both the pilot and main burners is shut off. The redundant valve solenoid may contain 2 separate coils, the pick and hold coils. Together, the pick and hold coils have enough strength to lift the redundant gas valve disc off of its seat. When there is a demand for heat, both coils are energized to open the valve. After the pilot heats up, the pilot's safety device de-energizes the pick coil. The hold coil remains energized to keep the redundant valve open. The pick and hold coils are designed with a safety feature so that if there is a momentary electrical or gas failure, or a short thermostat cycle, or any other malfunction that puts the pilot out, the hold coil will be de-energized, shutting off the gas to the pilot. The redundant valve cannot reopen when electricity is restored because the hold coil cannot open the valve by itself. The pick coil and pilot igniter cannot be energized until the pilot has cooled down, and the pilot safety device recycles the system through the pilot reignition sequence. Two-stage redundant combination gas valves are used to provide two different firing rates in furnaces for improved comfort and economy. The high fire stage provides full rated input and enables the furnace to properly heat the home on the coldest days. But on moderate temperature days, which usually occur more often, the furnace operates in the low fire stage to minimize on-off cycling and to provide more continuous warm air flow for better comfort. The low fire stage fires at about 70% of the high stage input. The basic operation of the two-stage redundant combination gas valve is the same as the single-stage combination valve described previously. The main difference is in the construction and operation of the gas pressure regulator. A third solenoid is used to set the pressure regulator spring to the high fire position, which is about 3.5 inches water column, producing full-rated gas input. When the solenoid is off, the regulator spring returns to the low fire setting, about 1.7 inches water column, producing 70% of rated input. The pressure regulator has two independent adjusting screws for setting the high fire and low fire manifold pressures. Now, let's look at some basic gas valve troubleshooting procedures. We'll start with a simple control system. The principles of this system also apply to more complex systems. In checking a simple automatic gas valve with a standing pilot, first be sure that the proper voltage is applied to the furnace and that the pilot is lit. Then set the thermostat up to demand heat and observe the burners for ignition, or listen for the gas to flow from the manifold. If either is observed, the valve opened. If not, you must check the valve. To check the valve, first verify that there are 24 volts across its terminals. If voltage is present, the problem is probably in the valve itself. If there is no voltage present, the valve will not operate. There must be a problem elsewhere in the electrical circuit. For instance, either the thermostat, high temperature limit switch, or the pilot safety switch could be open. You can check the voltage across their terminals to find the open circuit. Important: never short across valve terminals with a wrench or screwdriver to check for voltage. This type of abuse can burn out the coils in the valve, the thermostat anticipator, or the transformer. To check the valve, turn off the electricity to the furnace and remove one electrical lead from a valve terminal. Then connect an ohm meter across the terminals of the valve. If a readable resistance is obtained, the valve is probably okay electrically, but could be at fault mechanically. If an infinite resistance is read, the coil circuit is open, indicating a broken wire or burned out coil. If a zero resistance is read, the circuit is shorted. In either case, the valve must be replaced. To check for mechanical failure, such as a sticking valve, cycle the valve on and off and observe the burning operation. If the burners stay on after the valve is turned off, then it's stuck open. Often it closes if tapped lightly. However, this just confirms that it was stuck and is not a cure. The only solution is to replace a valve that has stuck, since it will probably stick again. This is a serious problem, since stuck gas valves can cause damage to the unit or the building. Any mechanical failure or electrical failure is grounds for replacement, since valves should never be repaired in the field. Caution: some valves with bimetal actuators take time to open and close. Be sure you give them enough time to operate before condemning them for failure to open or close. In this module, gas controls have been explained and discussed. A description of the operating principles of gas pressure regulators, manual gas valves, and various automatic gas valves and their actuators was included. The configuration and operation of several common types of automatic combination gas valves were also covered. The gas controls described in this module regulate and control the flow of gas from the supply to the orifice. In the broadest sense, gas controls also include ignition systems and safety and operating controls. These will be covered in the next two modules. Bear in mind as you review these modules that the gas controls, ignition systems, and safety and operating controls all must work together for proper furnace operation. In Module 6, Gas Ignition Systems, the function and operation of various types of ignition systems are included. The types of ignition systems discussed are standing pilots, reignition pilots, and direct ignition. Stop. Complete skills check number 2 in your workbook. Check your answers against the answer key. Identify those areas in which you need additional work. Use the paragraph references to review this material.